Good morning everyone, I am Mr. Ish. Thank you for joining me for this video. We are looking here at two questions only which will bring home the point that when it comes to integrals you have to learn to think outside the box. Not every integral question will very easily fall into the variety of techniques such as polynomial substitution or trigonometric substitution, integrating by parts, partial fraction decomposition, any of those number of techniques which we will look at or what we have already looked at, and some of the more complex techniques. Not everything very easily falls in those defined categories. Therefore, when it comes to integral questions, you have to learn how to think outside the box to solve them. The first example we look at, which drives home the point, is this. We're looking at the integral of this, e to root x dx. It seemingly looks easy, but it isn't. The part where you have to do thinking out of the box is you have to somehow rearrange this such that you can bring in integrating by parts technique. But how do we go about rearranging this? You have to use a modification of the polynomial substitution technique to reword this. And look how I will do it. You will have let a equals root x. I'm just using this letter a. It doesn't matter. You could use any letter. If a is equal to root x, solve for x and take the root on the other side. X is equal to a square. Now you take the derivative of this. You will have 2a dA is equal to dx. This set of substitutions, this one right over here, and this right here allows us to reword this. This will very likely play right in here, and dx will come right in here. So suddenly your entire integrand becomes as e to the a, and you have 2a dA. We can reword this out. 2 coming out as a coefficient, we have a e to the a dA. Now we have a product of two dissimilar functions in our integrand for which integrating by parts technique can come into play. U is equal to a, you know we have to do u, du and v. Du is equal to dA. That's why I was using a over here, because I would be using the u letter in the integrating by parts technique. And then v is the integral of what remains, which is e to the a dA, which must be still e to the a because the integrand e to the a leads to the antiderivative e to the a. You have u to the v, uv minus integral v du, bring everything into play. You have 2 and you close this parentheses. You have uv minus integral v du. You have a e to the a minus e to the a du is dA. This is easy. Open everything within the parentheses. You have a e to the a minus integrand e to the a leads to e to the a plus c. Resubstitute your a values. You'll have 2. A over here is right here, root x. As you can see, you have root x, e to the root x, you're resubstituting all of these a's which are right over here, minus e to the root x plus c. You can actually bring out e to the root x because it's a common term, and the final answer will be published right here. You'll have 2e to the root x, you'll have root x minus 1 plus c, and this will be our final answer for this question. And you can see how the question played out. You have to look at your integrand, because originally you cannot do integrating by parts technique here successfully, nor polynomial substitution as let alone procedures. You have to use polynomial substitution in a modified manner to reword your integrand to this, and you can clearly make it here into this integrating by parts question, and then you carry it through and then you resubstitute and come back to your final answer right here. This right here represents our last question, which also requires you to think outside the box, doing more than that what one might expect to do for a question of this nature. You could technically do polynomial substitution technique where you make that entire integrand your u and you continue from there. It technically can be done, but the entire question would become very complicated in terms of that rational function which will play through. The best thing over here is to use algebra to manipulate your integrand and make it easier. And this is what you can do. You use the properties of radicals and you look at something like this. 1 minus x divided by root 1 plus x. You rationalize the numerator. When you rationalize the numerator, you're multiplying it root 1 minus x and root 1 minus x. Suddenly this item in the numerator becomes 1 minus x because the roots go out. Here in the denominator, this is just like saying root a times root b is equal to entire root ab. You know the property of the radicals. Here you're looking at 1 plus x times 1 minus x, which is 1 minus x square, all within the radical. Now when you look at this algebraic manipulation, this represents our new integrand, and our question becomes this: 1 minus x dx over entire root 1 minus x square. You have a minus sign and everything can be split in terms of an integral across that minus sign, so you end up having just dx over root 1 minus x squared. You have this minus sign, and then you have a new integral. Now here you have an x over root 1 minus x squared dx. You can see how we've done this. We had something which looked like this, 1 minus x squared. We did this, and then we did this. Separation of these two integrals across this minus sign, and that's what we've done. Nothing too out of the ordinary here. This, when you look at it, is not hard by any means. You don't have to bring in the trigonometric substitution where you're looking at something of this form. You can, but you don't have to. A squared minus x squared, and here a equals 1, and x here is equal to sine theta, and dx is equal to cosine theta and d theta, and then take this through trigonometric substitution. You could, and when you did all of this, you'd end up getting arc sine x. You can do all that, but you don't have to, because if you think back to your library of antiderivatives or these specific sets of antiderivatives, and you think back to the fundamental theorem of calculus, the inverse relationship between derivatives and integrals, you know that anytime you look at something like this, inverse sine x, you always get this 1 over root 1 minus x squared as its derivative. You know that from your derivative videos, that the derivative of this is this. Therefore, the integral of this must be back, taking you back and giving you this. So all of this right here should technically just give you arc sine x, or you can say inverse sine of x, and this entire part is already done if you think of everything in that way. What really remains now here is the evaluation of only the second part, which requires a polynomial substitution technique. So we just set this first part aside, and we look at this second part. We have x over root 1 minus x squared. I know we have a minus sign over here, but we'll ignore that, this minus here. You do a polynomial substitution. U is equal to 1 minus x squared, du is equal to minus 2x dx, and dx is equal to minus du over 2x. This becomes here minus 1 over 2. I've pushed the 1 over 2 out. We have an x du over root u and x. These x's cancel out. You essentially have minus 1 over 2. I haven't forgotten about this minus. It'll interact with this minus and make it a positive, but we'll worry about that at the end. You have u to the minus 1 over 2 du. When you do the integral of that, you have minus 1 over 2 u to the 1 over 2 over 1 over 2, because it's minus 1 over 2 plus 1 divided by minus 1 over 2 plus 1. These will cancel out. 1 over 2, 2 over 1 will cancel out. You just have minus, and you'll have a root u. Initially, u here being 1 minus x squared, and this is what you have. This comes out of this second part with a minus sitting outside. This minus right over here. So we have the first part done, it's arc sine x. We have the second part done, and it's this. We just have to combine them together, and we will. For our finality, our answer is this. This first part giving me sine minus 1 x as my antiderivative. I have this minus right here, and the minus which came out from just this integral right here as its antiderivative. These minuses counteract, you get a positive, and I have a root 1 minus x squared plus c, and this right here is a good answer. You could take the derivative of this and you'll end up back right over here. Lastly, we'll just end with this. At any time you're looking at something which looks like this, 1 over 1 plus x squared, think back to your arctan derivative, and that'll be right here your antiderivative for anything which looks like this. Anytime you're looking at something which looks like this, 1 minus x squared, you're looking at inverse sine or arc sine. If there was a minus over here, you'd be looking at arc cosine. You know there's a 6 functions, we've looked at their derivatives. Just think them back. Take those derivatives and work them back, and whatever you get in terms of their templates will serve as the integrals, and those integrals will give you those inverse trigonometric functions, and these are your library of antiderivatives. These 2 plus the other 4, which you should keep in the back of your mind or in your reference sheet. So keep in mind, you have to think out of the box for many of these types of integrals. They seemingly look easy on the surface, but they tend to be quite complex, and you have to try to manipulate them however much you can to solve them out, and most of the times it's just experience, practice, and trial and error to solve these questions. Thank you for watching. Have a nice day.